Hi friends, and welcome to Lesson 5 here in our Kinetics, Thermodynamics, and Equilibrium unit. In Lesson 5 we're going to take a little bit of a pivot and we're going to start talking about spontaneity and spontaneous processes. And so here's a picture of a dramatic spontaneous process, which of course is this house burning down. And that is probably all you need to know to get into the lesson. So when we talk about spontaneous, we don't mean like the, oh, he's so spontaneous thing. We mean that these are chemical reactions that are going to proceed on their own once they get started. So once you start them, right, once you light the house on fire, the house will continue to burn unless you were to put it out. So anything that does this, where once you've started it continues, that is a spontaneous process. And that's going to depend upon two fundamental properties of that process. It's going to depend upon its change in enthalpy, it's delta H, and it's going to depend upon its change in entropy. So let's go in and take a look at both of these. So enthalpy is H. We already know this. We've talked about this quite a bit up to this point. It's the amount of heat energy stored in a system. We've been dealing with the enthalpy of substances, where we've been talking about the energy stored in the bonds that hold those substances together. Nature tends to favor reactions that undergo a decrease in enthalpy, that release energy or that are exothermic. Now, when we talk about nature favoring things, I know that sounds a little bit weird because it's not like nature is consciously being like, oh, that's an exothermic thing, I'm going to do that. That's not what it means. What we mean is that exothermic processes occur more frequently in nature without any additional input of energy. And that should make sense. You need to put energy into a process for it to be endothermic. So exothermic's taking energy out. It's much easier to let an apple fall on the ground than it is to throw that apple up in the air and keep it up there. In the same way, it's much easier to take energy out of a compound than it is to put that energy in. Think about a match. Does a match keep burning once it gets struck? And of course it does. That's because it's, among other things, an exothermic process. A little bit different is this notion of entropy, and I apologize because they do sound incredibly similar. But entropy is just a measurement of the disorder of a system or the degree of randomness in that system. And there's a lot of ways that entropy can increase, but for us, basically, here's what you need to know. As the temperature of a system increases, its entropy increases, the particles are moving more. And as we go from solid to liquid to gas, our entropy is increasing. And similarly, as we break bonds and make things that have fewer bonds that hold them together, our entropy is increasing. So here you can see we've got the three different phases of matter, and you can see that the entropy increases as we go from solid to liquid to gas. Does this make sense? If it doesn't, write down any questions you have before we move on. Generally speaking, nature favors reactions that undergo an increase in entropy, things that get more disordered. And this relates to the release of energy. If we're releasing energy from things, they're generally going to get more disordered than they were to begin with. Though, not always, and we'll talk about some examples. My question about the match is what happens to the entropy of our match as it burns? And if you think about it, we're going from wood to various particulate matter, carbon dioxide, water vapor, so the entropy of our match is increasing. So our match lights and continues to light. It's both favored exothermic and an increase in entropy. Both conditions are favored. Now, if you think about this, we've got two different variables in our situation. We can talk about changes in enthalpy and we can talk about changes in entropy. And each of them can do two different things. So there are really four different possible combinations we can have. Let's go through each one in turn. The first are exothermic processes that increase entropy. Exothermic processes are favored. Entropy increase is favored. Both of these conditions are favored. And so as a result, these processes will always be spontaneous throughout the universe. A good example of this is burning. Burning is an exothermic process that increases entropy. As long as oxygen and material to burn or fuel are present, this will always occur spontaneously once it starts. It will just continue to go without any additional input of energy. The opposite situation are endothermic processes that decrease entropy. Both of these conditions are not favored. As a result, these processes will never occur spontaneously anywhere throughout the universe. It doesn't mean that they don't happen. It just means that in order to get them to happen, you have to put energy in continually. As soon as you stop investing energy, the process will stop occurring. A classic example of this is photosynthesis, which, as you know, happens regularly on this planet, but it happens because of the input of energy from the sun. If the sun were to all of a sudden disappear, photosynthesis would cease, as it is not a spontaneous process and really never can be anywhere throughout the universe. So we've got our exothermic processes that increase entropy and our endothermic processes that decrease entropy. Then there are the two weirdo situations. So we can have exothermic processes that decrease entropy. You don't see a lot of these, but they definitely do exist. Here the enthalpy change is favored, but the entropy change is not favored. So is it spontaneous or not? That actually depends. It depends on the temperature. The temperature has to be low enough. Once that temperature is low enough, the process will occur spontaneously. Here's a classic example of that, freezing of water. So here's a magnified version of a snowflake. When water freezes, its entropy decreases, but when it freezes, we're removing energy from it. So it is an exothermic process that decreases entropy. As you're probably aware, water only freezes when the temperature is below 273 degrees Kelvin. Above that temperature, the process will not occur spontaneously. Similarly, we can talk about endothermic processes that increase entropy. In this case, the enthalpy change is not favored, but the entropy change is favored. And in these processes will only be spontaneous at high temperatures. The classic example of this is the opposite of what we just talked about, the melting of water. We had to put energy in to get that to happen, but the process does result in matter that is less ordered than it was to begin with. This only will occur spontaneously when the temperature is above 273 degrees Kelvin. Does this make sense? I hope it does. If you have any questions, write them down before we wrap up. Thanks so much for watching our discussion about spontaneity, entropy, and enthalpy. Make sure you can do the following things here at the end. Make sure you can explain the concept of spontaneity with regard to chemical and physical processes. Also make sure you can describe the changes in enthalpy and entropy that are related to spontaneous and non-spontaneous processes, and give explanations and examples of each of the 4 possible situations that we talked about in this presentation. If you can do those things, you're doing great. If not, that's okay too. Take a moment and write down any questions that you have. You can always leave them in the comments below the video, and you can always get in touch with me. Thanks again for watching. I really appreciate it. Have a great day.